This is a model of the Moon's orbit in 4 dimensions. Notice something? Hello everyone, and today I'm going to talk about the physics of orbital mechanics in more or fewer than 3 dimensions, and I will kind of make this the start of a possible series about why it might be that our universe has 3 dimensions, or 3 macroscopically visible relevant spatial dimensions, not counting the 4th dimension that time already is, and any dimensions that might exist but are essentially too small to be actually noted directly in macroscopic space. Now, what we are looking at is a modified version of my old orbital mechanics spreadsheet. I had actually made a numerical simulation of orbital mechanics in Excel because I thought it was fun, and Excel and similar programs may not be perfectly suited for this, but pretty much everyone has access to something similar, and I've actually probably I will put a download link to this spreadsheet in the description. And what I did back then was a basic numeric simulation of basic orbital mechanics and the orbit of the Moon around the Earth, and now I've modified this slightly to resemble a 4-dimensional or a 2-dimensional space. Now, the big difference is that the basic orbital mechanics we all know, that you might be familiar with, that you might have noticed that the image in the beginning looked somewhat wrong because it's not really symmetric and it isn't really periodic either. These basic orbital mechanics rely on gravity following the inverse square law, which isn't really an inverse square law as much as it is an inverse to the power of n minus 1 law, whereas n is the number of dimensions, which of course for us means that n is 3, so n minus 1 is 2, so to the power of 2 inverse square law. But in 4-dimensional space it would actually be an inverse cube law, and in 2-dimensional space it would be an inverse proportional law, and in 1-dimensional space it would actually be a constant law, if you want to call it that way. That's simply because gravity essentially spreads out in gravitational waves, and since these do not get dampened like audio waves where the air absorbs some of the energy, but gravitational waves just spread, their flow is essentially constant. That basically means that if you take any imaginary closed surface or hollow shape and put it around any gravitational source, so anything that has mass, then the integral of the gravitational field over that surface will always be the same, only depending on the mass of the object inside and the gravitational constant, not on the actual shape or size of the surface you put around it. And that means that if you take any sphere with the gravitational source or the object with mass in the center, then the gravitational pull at that sphere's surface has to be inverse proportional to the actual surface area of that sphere. And since the surface area of a 3-dimensional sphere is proportional to the radius squared, that gives you that inverse square law. But for a circle, the circumference of a circle is just proportional to the radius, not proportional to the radius squared. And a hypersphere's surface is proportional to its radius cubed. Of course, there are a few other things that would change with more or fewer dimensions. The gravitational constant itself unless you express it only in fundamental units, but if you express it in SI units, that has to be corrected as well. And it would seem that the mass of objects would also change, since obviously a four-dimensional sphere with a given radius could contain more particles than a two-dimensional circle with that same radius. But these are essentially proportional corrections that I've taken out of this model. I've just changed it to behave by the inverse to the power of n minus 1 law, and then put in the numbers to correct it so that it gives you, at least in the beginning, the same roughly almost circular orbit that we have in the three-dimensional lunar orbit model. Now, as you may have noticed in the images I've shown before or now, you can see that the two-dimensional model has this little circulation in argument of periapsis, but otherwise it's kind of stable. But it's long been theorized that a two-dimensional universe will be very simplistic and not really capable of forming the complex structures we know today. Whereas if you look at the four or five-dimensional simulation, now also with little changes to the orbit's original state, you'll see that it's very unstable. You're almost always either on an escape trajectory or on a collision trajectory, and the only really periodic or stable orbit is an absolutely perfectly circular orbit. Whereas the three-dimensional model, following the inverse square law, is a lot more practical to handle, and it is a lot more stable. It follows Kepler's laws. It's always either an escape trajectory or a periodic orbit. It's always symmetric and somewhat stable, and if you actually don't use numerical simulation, but if you actually want to go into the principles behind it purely mathematically and mathematically prove how these orbits behave, they are already a bit tricky, but much easier to handle than say four-dimensional orbits following the inverse cube law. And yes, by the way, it is okay to project all these orbits onto a two-dimensional plane. You can actually project all two-body problems onto a two-dimensional plane. That's also mathematically provable. Actually, not just independent on if it follows the inverse square law or the inverse cube law, but actually as long as you take any set of rules and you have a typical two-body orbital problem, even if you play around with changing the physics, as long as you don't have any chaotic component or any additional inputs like a third body or some kind of thruster, you can always project that orbit to a two-dimensional orbital plane without missing out on any interesting bits. That can also be extended if you have any n-body problem, and speed is of course relative. Then the input into this problem is always only 2 times n minus 1 vectors, because you can set the first object or any object as a frame of reference, and then you need one vector for relative position or distance to the other objects and one vector for relative velocity. So there are only 2 times n minus 1 vectors, and so the trajectory will always have to stay in a 2 times n minus 1 dimensional space or subspace. That is, in the case of a two-body problem, a two-dimensional orbital plane. Now, aside from being an interesting thought experiment, this can also be used as another hypothetical reasoning why the universe may have three dimensions. Again, using the argument that our universe has to be suitable for life, since if you assume that there could be several universes, then it makes sense that any intelligent life forms wondering about why their universe has as many dimensions as it has would obviously live in a universe suitable for life, because otherwise they wouldn't be there. And other thought experiments about how things might behave in more or fewer than three dimensions aside, this might deliver an explanation why universes with more than three dimensions would not really be suitable for life, because orbital mechanics would be inherently unstable, and therefore in such universe you might get stars or nebulae to form, but you would never have planets forming around stars, because there would be no stable orbits that these planets could have. Actually, any object that is anywhere nearby a star would, unless it is on a precisely circular orbit, be either on a collision course or on an escape trajectory, which means that any object would soon either be far away from that star or right in that star, which means that, assuming that a star's energy input is kind of necessary for life to be able to emerge, and that the inside of a star itself is not really an environment suitable for life either, that on any object you would never really have enough time for life to emerge without either drifting away from its star or falling into its star. Now this concludes our first little excursus into thought experiments and hypothetical physics in more than three dimensions. I am always open for requests or questions, and as always, thanks for watching.